Regular solids, also called platonic solids, are the most symmetric 3D shapes. There are only 5 of them: tetrahedron with 4 triangular faces, cube with 6 square faces, octahedron with 8 triangular faces, dodecahedron with 12 pentagonal faces, and icosahedron with 20 triangular faces. Each solid has the same regular polygon for every face, the same number of faces meeting at each vertex, and identical edge lengths. Think of a dice, a cube. Every side looks the same, and if you roll it, it can rest on any face with equal stability. Edge length: all edges are equal. Face angle: the interior angle of the polygon that makes up each face. For example, 60 degrees for triangles, 90 degrees for squares. Dihedral angle: the angle between 2 adjacent faces, which can be calculated using geometry. For a cube, it is 90 degrees. For a tetrahedron, it is arcos of 1/3, approximately 70.53 degrees. Symmetry: each solid can be rotated about its center and map onto itself many times. This high symmetry makes them ideal reference objects for teaching projection methods because the same rules apply uniformly to every edge and face. These properties let engineers quickly infer dimensions such as height, depth, and face-to-face distance without measuring each edge individually. Orthographic projection is like taking a photograph of an object from exactly the front, top, or side, but the camera does not have perspective. Parallel lines stay parallel. For a regular solid, we draw 3 views on the principal planes. Front XY shows height y and width x. Top XZ shows width x and depth z. Side YZ shows depth z and height y. Because a regular solid has equal edges, the 3 views are often similar. Example with a cube of edge A. Front view: a square of side A. Top view: also a square of side A. Side view: again a square of side A. For a tetrahedron, the front view is a triangle, the top view is a triangle, and the side view is also a triangle but with a different orientation. The rule is simple. Project every vertex onto the plane by dropping a line perpendicular to the plane. Connect the projected points in the same order as the real edges. This preserves true lengths only in views that are parallel to the edge direction. Otherwise, the edge appears foreshortened. A real-world analog: imagine a building on a grid map. The plan view top shows its footprint, the elevation front shows its height, and the side elevation shows depth. Each is an orthogonal view. Isometric projection is a way to draw a 3-dimensional object on paper so that the 3 principal axes appear equally foreshortened and the angles between them are 120 degrees. Imagine looking at a die turned so that 3 faces are equally visible. Each face seems to recede at the same rate. The scale factor, called the isometric reduction, for any edge not parallel to the view direction is k equals cosine 35.264 degrees, approximately 0.8165. This value comes from the angle between the line of sight and each principal axis, which is 35.264 degrees. Mathematically, if an edge has true length L, its drawn length L' equals k times L when the edge is not aligned with the view direction. Edges that are parallel to the view direction, for example the vertical edge when the object is rotated 45 degrees about the vertical, keep their true length because they lie along the projection line. Example, a cube of side 100 millimeters. In isometric view, the 3 visible edges on the front right top corner each appear as 100 times 0.8165, approximately 81.7 millimeters. The hidden edges are drawn with the same factor. This uniform reduction makes it easy to measure and compare dimensions directly on the drawing, because every non-parallel edge shares the same scale. Think of it like looking at a basketball through frosted glass that blurs everything equally. Distances shrink by the same amount in all directions that are not directly facing you. True length view shows the exact length of an edge as it would appear if you look straight along that edge. That is, the edge is parallel to the sight line. True shape view shows the exact shape of a particular face as if you were looking straight at that face. To obtain them for a regular solid, you rotate the solid until the desired edge or face becomes parallel or perpendicular to the projection direction. 1. Identify the edge for true length or face for true shape. 2. Rotate the solid about the appropriate axis so that the chosen element aligns with the line of sight. For a cube, Rotate 45 degrees about the vertical axis to make a space diagonal appear as a true length. 3. Project orthographically onto a plane because the element is now parallel to the sight line. Its projected length equals its actual length, and the face appears undistorted. Example, a regular tetrahedron has an edge of 50 millimeters. If you rotate the tetrahedron so that one edge points directly toward you, the orthographic front view will show that edge as a straight line of 50 millimeters, the true length view. Similarly, rotate until one triangular face is parallel to the picture plane. The drawn triangle will be an equilateral triangle of side 50 millimeters, which is the true shape view. Real-world analogy: holding a ruler directly in front of your eye shows its true length. Tilt it and it looks shorter. The same idea is used to produce engineering drawings that convey exact dimensions without any foreshortening. Auxiliary, also called auxethetic projection, is used when a face of a regular solid is inclined to the principal planes, making its shape appear distorted in orthographic views. By projecting onto an auxiliary plane that is parallel to the inclined face, the face is shown in true shape. Well, steps. 1. Determine the inclination angle of the face with respect to a principal plane. For example, a cube face inclined 30 degrees to the XY plane. 2. Draw an auxiliary plane that is parallel to the inclined face. This plane is often represented as a tilted rectangle attached to the principal plane. 3. Project the vertices of the solid onto the auxiliary plane using lines perpendicular to it, or along the same projection direction as the original orthographic view. 4. Connect the projected points. The inclined face now appears as an undistorted shape. Mathematical example: consider a regular octahedron with a face inclined 45 degrees to the front plane. The auxiliary plane is drawn at 45 degrees to the front plane. Using similar triangles, the true length of the face edge is recovered. Projected length L equals a times cosine 45 degrees. Solving for A equals L divided by cosine 45 degrees. Think of it like holding a piece of paper, the inclined face flat against a window, the auxiliary plane. When you look through the window, the paper looks normal, even though it is slanted relative to the wall. Hidden line removal, abbreviated HLR, tells you which edges should be drawn solid, dashed, or omitted, so a viewer can understand the solid's shape. For regular solids, the rules simplify because of symmetry. If an edge belongs to a face that is fully visible in the current view, draw the edge as a solid line. If an edge belongs to a face that is partially hidden, draw the portion that is behind the visible part as a dashed line. If an edge lies on a face that is completely hidden, omit the edge entirely. A special case is for regular solids. Cube, in the front view, 3 faces are visible. The 3 edges bordering the hidden rear face are drawn dashed. Tetrahedron, only 3 faces can be seen at once. The edge opposite the visible vertex is hidden and drawn dashed. Octahedron, in an isometric view, 4 faces are visible. The edges of the 4 hidden faces are drawn dashed. The purpose is to avoid confusing the reader with extra lines that suggest surfaces that are not actually there. A practical analogy is a 3D printed model. You can see the front surfaces. The back surfaces are hidden behind the material, so you would not draw them. Direction cosines link a 3-dimensional line to a projection plane. For a line with vector v equals v sub x, v sub y, v sub z, the direction cosines are L equals v sub x divided by the magnitude of v, m equals v sub y divided by the magnitude of v, n equals v sub z divided by the magnitude of v. When projecting orthographically onto the xy plane, the projected length L sub xy of a true length L is L sub xy equals L times the square root of L squared plus m squared equals L times cosine theta sub z, where theta sub z is the angle between the line and the z-axis, the axis normal to the xy plane. Similarly, onto the xz plane we use the square root of L squared plus n squared, and onto the yz plane we use the square root of m squared plus n squared. Example for a cube edge of length that makes a 30-degree angle with the x-axis and lies in the xy plane. L equals cosine 30 degrees equals 0.866, m equals sine 30 degrees equals 0.5, n equals 0. Projected on the xy plane, the length is a, since the edge lies in the plane. Projected on the xz plane, the length is a times the square root of L squared plus n squared equals a times 0.866. That is, the edge appears foreshortened. These formulas let engineers compute exactly how long a line will look in any orthographic view without having to draw it first. Using rotation matrices, any point x, y, z of a regular solid can be turned into a 2D projection by first rotating the solid to the desired orientation, and then dropping the z coordinate or applying an orthographic projection matrix. A typical workflow: choose rotation angles alpha, beta, gamma about the x, y, z axes. Form the rotation matrices. R sub x of alpha equals a 3x3 matrix with first row 1, 0, 0, second row 0 cosine alpha negative sine alpha, third row 0 sine alpha cosine alpha. R sub y of beta equals a 3x3 matrix with first row cosine beta 0 sine beta, second row 0, 1, 0, third row negative sine beta 0 cosine beta. R sub z of gamma equals a 3x3 matrix with first row cosine gamma negative sine gamma 0, second row sine gamma cosine gamma 0, third row 0, 0, 1. Combine them in order. R equals R sub z of gamma times R sub y of beta times R sub x of alpha. Multiply each vertex vector p, which is the column vector xyz transpose by r to get p prime equals rp. Apply orthographic projection onto the xy plane by discarding the z component. X prime comma y prime equals p prime sub x comma p prime sub y. For an isometric view, set alpha equal to 35.264 degrees about x and beta equal to 45 degrees about y. Gamma equals 0. This yields the classic 120-degree angles, and the scale factor k equals cosine of 35.264 degrees. The whole process can be coded in CAD software or a spreadsheet, allowing quick generation of accurate 2D drawings of any regular solid. Real-world analogy: rotating a cube on a tabletop and then casting its shadow onto a wall. The shadow is the 2D projection, and the rotation matrix tells you exactly how the cube must be turned before the light, the projection direction, hits the wall. Example 1. A cube of edge 120 mm is to be shown in true shape of one face and its isometric view. A solution steps: true shape, rotate the cube 45 degrees about the vertical axis so that a square face becomes parallel to the picture plane. Draw a 120 mm by 120 mm square. Isometric view. Apply rotation angles 35.264 degrees about x and 45 degrees about y. Compute scale factor k equals 0.8165. Each visible edge equals 120 times 0.8165, approximately 98 mm. Draw the three edges meeting at a corner with 120 degrees between them and label hidden edges as dashed. Example 2. A regular tetrahedron with edge 80 mm, required to show a true length view of a space diagonal. A solution steps: identify the space diagonal, connect two opposite vertices. Its true length is L equals square root of 3 times approximately 1.732 times 80 equals 138.6 millimeters. Rotate the tetrahedron so that this diagonal aligns with the line of sight. In the front orthographic projection, the diagonal appears as a straight line of 138.6 millimeters. The other edges are drawn as foreshortened using direction cosines. Angle 54.74 degrees to the view direction. Scale cosine 54.74 degrees, approximately 0.577. Example 3. Auxiliary projection of an inclined face of a dodecahedron. Face angle 58 degrees to the xy plane. A solution steps: draw the principal front view showing the inclined pentagonal face as a distorted pentagon. Construct an auxiliary plane at 58 degrees to the xy plane, tilted rectangle attached to the front plane. Project the vertices onto this auxiliary plane using lines parallel to the view direction. The projected pentagon will be regular with side length equal to the true edge length. Measure it directly. Tips for exam success: 1. Memorize the 5 regular solids and their key angles, dihedral angles. 2. Practice rotating objects mentally. Use the 45 degrees by 45 degrees by 90 degrees triangle trick for isometric view. 3. Always start with true shape or true length views. They give the exact dimensions needed for later foreshortened views. 4. When hidden lines are required, first draw all edges, then apply the HLR rules to convert appropriate edges to dashed. 5. Use the direction cosine formulas for quick calculation of projected lengths. They avoid trial and error drawing. 6. For auxiliary projections, keep the auxiliary plane parallel to the inclined face. This guarantees true shape.